What if you could have the speed of C++ without the memory bugs? What if you could build system software without fearing crash, data erase, or security exploit? In 2010, a new programming language appears, says fast and fearless. This is the story of Rust, the language that promised memory safety without a garbage collector. From a side project to powering browsers, blockchains, operating systems, and event-based software. This is the story of Rust. Before Rust, system programming was dominated by C and C++. This language was incredibly powerful. They run operating systems, game engines, databases, browsers, but they have a dark side. Memory bugs, buffer overflow, use of the free arrows, null pointers, these references, and data arrays. For decades, this bug caused crash, security vulnerabilities, and massive exploit. In fact, a huge percentage of critical security issues in major software projects came from the memory safety problems. The industries needed something better. In 2006, a developer named Graydon Hoare began working on a personal project. He was frustrated. Programming kept crashing because of memory bugs. He believed there had to be a ways to design a language that prevented this issue at compile time. In 2009, Mozilla began sponsoring the project, and in 2010, Rust was officially announced to the world. It wasn't just another C++ competitors. It introduced a completely new ideas, ownership. Rust's biggest innovation is its own ownership system. Instead of using garbage collectors, Rust enforces strict rules at compile time. Every value has its own owners. Values are dropped when the owners go out of scope. Borrowing's rule prevent the errors. The Rust compiler acts like a strict teacher. If your code might cause a memory bugs, it refuses to compile. This concept eliminates dangling pointers, double free, and the errors without sacrificing performance. That's what made Rust revolutionary. Memory safety without garbage collection. Mozilla wasn't finding Rust for fun. They wanted to build the next generation browser engines. Their project was called Zobo. Zobo aims to create a safer parallel browser engines. Part of the servers eventually made the way into Firefox. Rust proved itself capable of handling massive code-based, high-performance renderings and multi-threaded system. It wasn't just theoretical anymore. It worked. Rust began gaining serious attention. Major companies started adopting Microsoft, Amazon, Google, and Meta. Microsoft even announced Rust as a part of a effort to reduce memory-related vulnerabilities in Windows. Cloud platforms began using Rust for performing critical components. Blockchain projects embraced it. Game developers experimented with it. Rust wasn't just safe, it was fast. Benchmarks often show performance comparable to C++. Something unusual happened. Year after year, Rust top developers away as the most loved programming language. Developers prize its truth, its documentations, its errors, mistakes, and its communities. Rust made low-level programming feel modern, structured, and clean. Rust didn't try to replace every language. It targeted one domain, system programming. Compared to C++, C++ offered decades of libraries and ecosystem maturity, but Rust offered guarantees memory safety, fearless concurrencies, and modern package management. Rust makes entire classes of bugs impossible, not discouraged, impossible, and that's a powerful promise. Rust expanded beyond the system programming. It enters WebAssembly, embedded devices, blockchain ecosystem, and game engine. It became a popular language for writing CLI tools. Its compiler produces fast and standalone binaries, and its ecosystem continued to grow rapidly. Rust's future looks strong. It's being integrated into operating system. The Linux Foundation support Rust initiative. Part of the Linux kernel now accepts Rust code, a historic switch from C dominance to a sister alternative. Rust may not replace C or C++ overnight, but it's carving out its place steadily and confidently.